Hello, everybody. We're starting chapter 4 today on work and machines. Now, we've got 3 pages of notes to get to today, and it may just go over 33 minutes. I hope not, but it might. If it does, whatever goes over 33 minutes, that'll be a separate video because it stops recording and makes a new one at that point. I don't know why. So let's hope it doesn't. All right, so we're talking about work and machines. And the main idea for this particular section is that machines make doing work easier or faster, one or the other, maybe both, by changing the force that you're using, okay, by changing the force that you're using that's needed to do the work. Okay, now before we can actually start talking about the machines themselves, let's talk about work. What in the world is work? And no, it's not the job you go to. Work is an actual physics quantity. It's denoted with a capital W in the formulas, and it's measured in a unit called the joule, Joule, for James Prescott Joule. Okay? You use this a lot in chemistry and physics. Now, what is work? Work is a force applied through a distance. So something has to move and a force has to do it. Now, just because a force is exerted on an object doesn't mean the object moves. If a force is exerted and the object doesn't move, that force is not doing any work. But if the force is exerted and the object does move, then it's possible that force is doing work. But there is a requirement for that particular force to do work. And that is that the direction of the force, let's write that down, and I'm going to use all caps right here. The direction of the force must be parallel to the direction the distance the object is moved. It has to be parallel to the distance. Now, what is parallel? Well, you should know that if objects are parallel, that means they're side by side and they never cross. If you have 2 lines, or in this case, 2 arrows that are side by side and they never cross, they're parallel. They stay the same distance apart. Okay, so this is a force, a horizontal force, and here's a horizontal distance. So both the force and the distance are parallel to each other. Now, this is a symbol we use in geometry for parallel. So the force is parallel to the distance. So this force is doing work. Okay? Look at this example. Somebody is pushing a crate up an incline, and it travels a distance up the incline. Both of these arrows are parallel. Since the force is parallel to the distance, work is being done. Now, this last one's a little different. This person is pulling the wagon, but the wagon's handle is at an angle. So the person is actually exerting their force at an angle. But the distance is horizontal. That's okay. Think about it a moment. When you pull something, you pull in 2 directions at the same time. You pull out or forward, and you pull up slightly as well. Not enough to make the object leave the floor, but you do pull up. So out and up. The up part does no work, but this part right here, this part is parallel to the distance, so this part of the person's force does do work because it's parallel. Now, are there times when forces can be exerted, but they don't do work even though there's a displacement? Certainly. Look at this. Here, the person is holding the box by pushing up on it to keep it from falling. So they're pushing up on the box, but they're walking forward. Notice that in this case, the force and the distance are perpendicular or at 90 degrees. They make a right angle, a 90-degree angle, just like the corner of a square with each other. So since the force is perpendicular, this is the symbol for perpendicular, the force is perpendicular to the distance, so the work equals 0. Only when the force, or maybe part of the force, is parallel to the distance is work done, okay? So there must be a displacement, or must be a distance traveled by the object, and the force must be parallel to the distance. Now, how do we calculate the work done by a particular force? That's actually very easy. Work is simply force times distance, or if we use the symbols, F times D. So there is the formula for calculating work. And look, I've put it over here in one of our formula triangles. So if you're looking for the work, you're going to say F times D. If you're looking for the force, you're going to say W divided by D. If you're looking for the distance traveled, you're going to say W divided by F. Okay? All right, so let's look at this example. Now, suppose that you do 50 joules of work. Okay, so we know how much work we're doing. We're doing a work of 50 joules to push a flatbed dolly loaded with merchandise a distance of 35 meters through the store. So the distance we're going to exert our force, whatever it is 35 meters. So we know the work done and we know the distance the work was done over. How much force did we exert to push the dolly? So we want F, the force. All right, so we come over here, cover up the F. We want to say W, or work, divided by D, distance. All right, so let's write that down. The force equals W, the work, divided by D, the distance. So we're going to put the work on top, and we're going to put the distance on bottom. Now, if you've got your calculator, go ahead and stop at this point. Put it in yourself. Make sure you're not putting it in backwards. I've seen a lot of people putting things in backwards. The top number always goes in first. You hit divide, and then you stick in the bottom number, and then you hit equals, okay? See if you can get the right answer. Okay, if you've stopped for a moment to try that, you should have gotten a value of 1.4 newtons. So that is the amount of force. That was step 3, by the way, is writing down the answer with the unit. Sorry about that. So the person exerted 1.4 newtons of force to push the dolly 35 meters and therefore did 50 joules of work. Okay? Now, let's continue on a little bit. Let's talk about how work and machines are related. So let's take a look. A machine is simply a device that helps us do work by increasing the amount of force we exert. So that's one thing it can do. All right? Or increasing the speed of the object being worked on. So that's 2 things a machine can do. Sometimes they'll do both. Okay? So let's take a look. A simple machine. We're going to talk about 2 types of machines, simple and compound. A simple machine is a machine that has very few parts. In other words, it's simple. And it usually requires only one movement of the machine. Now, we're going to list the examples. There are 6 simple machines, and we're going to list them. All right? The first is the inclined plane. You know, a ramp. That is one type of simple machine. Another simple machine is the wedge. like the head of an axe or a doorstop wedged underneath the door, okay? There's also the screw. And there is the lever. And there's the pulley. And finally, there's the wheel and axle. Okay? A wheel and axle. Now, of these 6 types of simple machines that we have, these 2 are actually modified inclined planes. They just don't work quite the same way as a regular inclined plane. A screw has a little shelf that stands out and goes all the way around the screw, all the way up, like a helix of DNA. Goes around and around and around, and that is like a ramp. Okay, and an ant, of course, screws are small, so an ant could walk up around and around and around that ramp and come up to the very top. So that is a modified inclined plane. A wedge is also a modified inclined plane, okay? It's used to split things, for example, and we're going to look at that in just a minute. But these are the 6 types of simple machines, and these 2 are basically just modified inclined planes. All right, now, what is a compound machine? Let's take a look. The next page, if you print it in color, it's really colorful. Okay, a compound machine is a machine that is combined from 2 or more simple machines. Okay, so it's 2 or more simple machines being used together. So now, if you look at this little poster that I made smaller and put on here for you, here are the 6 simple machines. An inclined plane, the wedge, and the screw. And notice the wedge is much like an inclined plane, except that a wedge can come up off the ground. An inclined plane stays on the ground, and it tapers both sides. So there's no 90-degree angle right here in any of them. They're all different angles, okay? Here's the screw. It's got an inclined plane wrapped around the cylinder of the screw. So you could have a little ant that could walk up all the way around, all the way up to the top. Okay? We'll see how they're used in a minute. So those are the first 3. Then you also have a lever. Like a lever could be used like a crowbar or a seesaw, or if you've ever taken a paper clip to pry a button battery out of its casing, that's using a lever. Okay? Wheel and axle. It's a wheel attached to a bar so that they rotate together. Okay? Think about it a moment. Where can you think of a wheel and axle you know about? How about your car? Your car has wheel and axle. Okay, a pulley. A pulley is a wheel with a belt or rope or string or chain wrapped around it so that it will turn as you pull the rope or chain or string through. Compound machines are made up of 2 or more simple machines. A wheelbarrow has a wheel and axle, and it also has a lever, okay? Because when you pick it up, the lever, the fulcrum of the lever is right here. The fulcrum is the point, and I think it shows it right here. Yes, the fulcrum is the point about which the lever rotates. In other words, this is the fulcrum in each of these cases. The fulcrum, F-U-L-C-R-U-M, the fulcrum is what makes it rotate about a point, okay? A pencil sharpener has wedges inside. They're the little grooved wedges that sharpen the pencil. They're actually angled, and it has a lever here that you turn to make it turn inside, and it also contains a wheel and axle. The wedges and the wheel and axle are inside. You can't see them. The crane uses a pulley, uses a lever, and uses a wheel and axle. Okay? A bulldozer uses a wedge, a lever, and a wheel and axle. Look at these clippers like you prune your bushes with. Has wedges. Scissors are nothing more than wedges. And it has a lever. When you squeeze, you're doing a lever. The fulcrum is right here, the screw. An escalator. Inside, there are pulleys that make pulley belts that make the stairs go up, disappear, come down, and go up again. All right? And then you have an inclined plane, which is what the entire staircase is. It's sort of an inclined plane, isn't it? How do we know how well a machine works? All right, that's the next one. How do we know how well a machine works? Well, basically, by how efficient it is. Well, what does that mean? How are we going to know how efficient a particular machine is? Well, efficiency is actually a mathematical quantity. So let's look. Efficiency. E-F-F-I-C-I-E-N-C-Y. Efficiency. And we use a lowercase letter e to represent efficiency. Efficiency is a ratio. So yes, it's mathematical. It's the ratio of output work to input work of a machine. It's usually measured as a percent. So we typically multiply the ratio by 100 to make it a percent. Now, the greater the efficiency value is, the better the machine is. Is there such a thing as a machine that's 100% efficient, which would be an ideal or perfect machine? Well, actually, no, there isn't. In order for a machine to be 100% efficient, the input and the output work would have to be the same value. And that's never, unfortunately, in reality, that's never going to actually be possible because of things like friction between the parts. Friction reduces efficiency. And since whenever you have parts moving against each other, you're going to have friction, you can't have, in reality, a machine that is 100% efficient. Although we can get very high efficiencies by using things to reduce friction, obviously. So let's write out the formula. It said efficiency E equals the work out divided by the work in. Now, what does that mean? The work out and the work in. Well, let's take a look. Oh, I almost forgot one thing. Remember, we're going to make this a percent, so we have to multiply by 100 to do that. Okay? So this is the formula for efficiency. Now, about the work out and the work in. Let's take a look. The work put in to the machine is what you do. You do to the machine. You put in work, or you put work into the machine. You do something to the machine. Then, in return, the machine does work for you on the object to be moved. So the work out is what the machine, whoops, I forgot the C in machine, what the machine does to the object, the one to be moved. Okay? So work in is what you do to the machine, and you get work out of the machine on the object to be moved. Now, I also have a triangle, a formula triangle for this, but I couldn't fit the word out in. It kept going down to a second line because I have to make it so small. So we have to put the word out in here ourselves. So efficiency equals work out divided by work in, and don't forget the times 100 to make it a percent. In fact, what we could do is do this. Efficiency equals work out divided by work in times 100, okay? So let's take a look. Now we're going to look at this example. It says, suppose that you do 20 joules of work in pushing a crate up a ramp. Okay, if that's what we're doing to push the crate up the ramp, we need to call it the work in. So work in equals 20 joules. All right, that's what we do. Now, the output work from the ramp is 11 joules. And we want to know what is the efficiency of that inclined plane. Okay, well, let's take a look. We want to find the efficiency. So that's going to be work out divided by work in times 100. All right, so the efficiency equals work out divided by work in times 100. So that's going to be 11 joules over 20 joules. And notice what happens to the units. Boom, boom, they cancel out, don't they? How about that? Times 100. Okay, now, if you will take 11, divide by 20, and then take that and multiply by 100, we'll have the efficiency. So real quickly, why don't you go ahead and stop the video, try it on your calculator, and see if you can get it before we go on. All right, so if you have put the numbers into your calculator, you should have gotten 55% efficiency. Okay, 55% efficiency. Why is it not more efficient? Well, probably because if you're going to push a crate up a ramp, the bottom of the crate is moving against the top of the ramp, the surface of the ramp, and you're going to get a lot of friction. So some of the work you're doing is being converted into heat by friction, and therefore you're not going to be 100% efficient. Only, in this case, 55% efficient, all right? But notice that even though the work out and the work in are not the same, it's still easier to use the ramp, okay? I'll tell you why. If it's a crate and you're trying to lift it up to a height, you would have to actually use a force equal to the weight of the crate to lift it up to a height. You might not be able to use that much force. The crate might be too heavy. So you use a ramp to get it up to the height you want. All you have to do is push the crate up the ramp. You don't actually have to lift it, all right? So even though you may have to push the crate farther than what you had hoped, all right, you don't have to use as much force. So that's one of the things about machines, okay? How are they useful in doing work for us? They change the amount of force we exert, okay? Another thing they can do, they change the direction of the force. And I'll show you an example of that here in just a minute. They change the direction of the force, or they exert the force faster. In other words, they make the object go faster. So let's take a look. Here's an example of the last one. A bicycle does work to move your body from one place to another, okay? When you put in work, it moves you a distance. Now, if you pedal faster, think about this for a second. If your foot pumps around once on the pedal, because of the gears, which are more or less wheel and axles on the and pulleys on the bike itself, they actually turn the wheel further than one rotation. So your foot may be going around once, but the wheel is going around a lot more than once. It may be going around twice or 3 times for every one of your pumps. So you can increase the speed at which you travel. Here, the man is trying to lift the car on a jack. Now, he can't lift that car himself to change the tire, so he has to use a jack to do it. Now, he exerts a small force on the end of the jack over a longer distance, and the jack exerts a much larger force over a much shorter distance, but it lifts the car because it's more force. May not lift it as far, but it changes your little force into a big force. All right? In fact, that's the trade-off for getting a bigger force out of the machine. We may have to exert our force over a larger distance, but it's smaller than the force that we get out. Okay? Look at this wedge. This wedge is changing the direction of the force. All right? The axe, when you swing the axe, the force is actually down into the wood, straight down. But because the wedge, the sides of the axe get further apart, it pushes apart the wood on each side. So it pushes one side this way and one side this way as it goes down because the wedge itself gets wider. It's narrow here and wider here. So it changes the direction of the force exerted on the object and allows the wood to split. So here we have an example of a machine increasing the speed at which the object moves, increasing the force the machine exerts, increasing it from what you put in to what it puts out, or changing the direction of the force. Okay? Now, so you might want to underline this. Machines exert larger forces over smaller distances, yet we exert a smaller force over a larger distance. That's the trade-off right here. Now, one last thing I want to talk about. In this case right here, where it changes the size of the force, we can talk about the mechanical advantage of a machine. Okay? Some machines will increase the amount of force that we put in by a bigger value than other machines. And that's called the mechanical advantage. It's the effectiveness of the machine. It's also a mathematical quantity. It's a ratio, so that means we need to put a little ratio bar right there. So mechanical advantage is the ratio of the force the machine puts out, the output force, divided by the input force exerted by the person. Okay, so Fn, what you do versus what the machine does. This is how we find mechanical advantage. Okay, so, whoops, I want to keep the red. This is what you do, what you exert, and this is what the machine exerts on the object to be moved. Okay? So you want a mechanical advantage that is greater than 1. If the mechanical advantage is less than 1, that means the force in is greater than the force out. And what would be the point of that? A machine that doesn't even use as much force as you do, you might as well do the work yourself. So you always want the force out, the force that the machine exerts, to be greater than what you exert on the machine. So this number needs to be a number greater than 1. So let's look at this example right here. Suppose you decide to use a pulley system to lift a crate that weighs 950 newtons. This means you want the pulley system to lift that weight, which means it has to use a force equal to that. So we want the pulley to output a force of 950 newtons, the weight of the crate, to lift it, okay? Because you can't lift that, I can't lift that, I don't know anybody that can lift that, all right? So now, we want the pulley to put out a force of 950 newtons. What are we going to put in? we're going to put in only 250 newtons by pulling on the rope of the pulley. Then the pulley will lift the crate. We want to know what's the mechanical advantage of this particular pulley system. Okay, well, mechanical advantage is the force out divided by the force in. So in this case, that's going to be 950 newtons that the machine does divided by the 250 newtons of force that we exert. Notice what happens to the newtons. They cancel. So mechanical advantage is just a number, a factor. In fact, it's how many times more force this one has than this one. So let's take a look. Take your calculator and divide 950 by 250. If you want to stop the video for a moment and do that, go ahead. Okay, if you've divided, you should see that the mechanical advantage of this particular machine is 3.8. Okay, so that means the output force is 3.8 times bigger than the input force. Okay? So it multiplied your force by 3.8 to get the force it exerted on the crate. Okay? So it's just, the mechanical advantage is just a factor, a multiplier. Isn't that kind of cool? You just always want to remember the force you get out from a machine should be larger than the force you put in. Otherwise, what's the point, right? That's what the machine is for. Okay, you guys have a good evening, and I hope this video is not that long, and we'll see you. Bye-bye.